Hello everyone! Sa discussion na to, magbibigay tayo ng additional examples for the convergence test for series of non-negative terms, specifically sa integral test and sa comparison test. Kung di nyo pa napapanood yung lecture video, panoorin nyo muna yon. Pero kung familiar na kayo sa dalawang test na yon, then we can proceed with our recall of the concepts. Tapos, we move on to solving our exercises. So, let's begin with the integral test. Applicable lamang yung integral test kapag meron tayong function na continuous, positive valued, at decreasing sa isang interval k to positive infinity, provided that our f of n is equal to an on that interval. So kapag nasatisfy natin yung mga conditions na yon, pwede na nating i-compute tong improper integral, and if it converges, then our series converges as well. If it is equal to positive infinity, then our series would diverge. Yung next test natin, comparison test, involves two series of non-negative terms an and bn. Kung si an and bn has this kind of relationship where an is less than or equal to bn, tapos yung bigger series natin is convergent, then yung smaller series should converge as well. On the other hand, if yung relationship is such that an is greater than or equal to bn, tapos yung smaller series natin is divergent, then yung bigger series natin should diverge as well. Sa comparison test, pipiliin natin si bn or our series for comparison. So, it is helpful to keep in mind the following series which we know the convergence or divergence of. Yung una is P series, which converges kapag si P is greater than 1. Tapos nagda-diverge siya kapag P is between 0 and 1. Kapag si P equals sa 1, it gives us the harmonic series, which we know to diverge. Additionally, alam natin yung geometric series, where nagko-converge siya kapag yung absolute value ng ratio natin is strictly less than 1. Otherwise, divergent siya. So ngayon na na-refresh na tayo about our topic, pwede na nating silipin yung mga exercises na ating sasagutin. So meron tayong 10 exercises and we are asked to determine whether these series are convergent or divergent using either integral test or comparison test. You might want to pause the video first, tapos sagutin nyo muna on your own before nyo tignan yung solutions ko. Okay, let's start with exercise 1. So, ang binigay sa ating series is the sum from 2 to infinity ni ln n over n. So, pipili tayo between integral test or comparison test, since yun yung topics natin ngayon, kung alin yung i-apply natin dito sa series na to. Since ln n over n ay easily integrable, then try natin i-apply si integral test kasi it's useful for those types of series. So, let's define f to be ln x over x para si f of n equals sa an on our interval 2 to infinity. Tapos, clearly, this function is continuous and positive valued on our interval. Moreover, decreasing siya kasi kapag kinuha mo yung derivative, you will get 1 minus ln x over x squared. And ln x is greater than 1 whenever x is greater than 3 kasi ln e is equal to 1. E is approximately 2.71. So you're expecting this to be less than or equal to 0 on the interval 3 to infinity. Pero magkaiba to with our given interval. But that doesn't matter. In fact, the conditions for integral test and comparison test only needs to be satisfied eventually. So hahanap lang tayo ng k wherein satisfied sila. And this time we have 3 to infinity. So let's just change this to 3 to positive infinity. So now, satisfied na yung condition natin for integral test, we can conclude that the integral test is applicable. So, i-apply muna natin. i-compute natin tong improper integral na to, which is just the limit as t approaches infinity ng integral na to. And again, si ln x over x is easily integrable if you let u to be ln x. Exercise nyo na lang yon. And if you do it, you'll arrive at the antiderivative ln x squared over 2, which we will evaluate from 3 to t, giving us ln t squared over 2 minus ln t over 2 squared yung ln 3. Now, if we approach t to positive infinity, si ln t, pupunta din siyang positive infinity. So, this first term goes to infinity, and this is just a constant. So, finally, yung improper integral natin should just be infinity. But that is the second case of integral test. So, we can conclude by integral test that our series is divergent. In fact, the series from 3 to infinity. But again, removing the first few terms of our series does not affect its convergence or divergence. So, pwede natin i-conclude na yung from 2 to infinity should also diverge. So, we have proven it using integral test. Can we apply comparison test on this series? Well, we can try. So, let's do that. For comparison test, hahanap tayo ng series to compare our given series with. So, since alam natin na divergent yung series na to from our integral test, pwede tayo maghanap ng divergent series within AN. And since we can see the harmonic series 1 over n, let's try that first. We will be using the divergent harmonic series 1 over n, sum from 3 to infinity. I started at 3 para ma-invoke natin yung idea na si ln n ay greater than or equal to 1 for n greater than or equal to 3, which we used previously. So, kapag dinivide mo by n both sides, you have ln n over n greater than or equal to 1 over n. So, we arrive at an inequality wherein yung ating smaller series is divergent, which is case 2 ng comparison test, and hence we can conclude that itong series na to should be divergent, and hence yung original series natin from 2 to infinity would also diverge. So indeed, yung series natin is divergent. Moving on dun sa exercise 2, we are given the sum from 1 to infinity ng 1 over n squared sine ng 1 over n. And we can see that this is easily integrable kung ilalet mo si u to be 1 over n, no? Kasi ito na yung derivative niya. You're just missing a factor of negative. So let's try applying integral test. We let f to be 1 over x squared sine 1 over x. Para yung f of n natin equal sa an for our interval 1 to infinity. Tapos clearly naman, continuous yung f natin, and yung positive valuedness niya, we can argue na kapag si x greater than or equal to 1, yung 1 over x mo would be between 0 and 1. So yung sine 1 over x natin would be between 0, and in fact it's sine 1, but sine 1 is less than 1. So sine 1 over x would be between 0 and 1. Moreover, si f natin is decreasing using the same logic. Si cosine 1 over x would also be between 0 to 1, as well as yung sine 1 over x. And if we take the derivative of f, we will arrive at this equation. Tapos kapag finactor out natin, we will just be left with cosine 1 over x, which we know to be positive, plus 2x sine 1 over x, and this is also positive. X to the 4 will also be positive. So this entire equation would be positive on 1 to infinity. So we're taking the negative of that. We're ensured that this is less than or equal to 0 on our interval. Hence, integral test could be applied. We can now solve for the improper integral. This is just the limit as t approaches infinity of this integral. So again, this is easily integrable when you let u to be 1 over x. And if you do that, you will arrive at the following antiderivative cosine 1 over x. And if we evaluate that from 1 to t, we will arrive at cosine 1 over t minus cosine 1. Now, approaching t to infinity, yung 1 over t magiging 0. So, yung cosine 0 ay 1. So, finally, our improper integral would just be 1 minus cosine ng 1. So, since yung improper integral natin nagko-converge, which is case 1 ng integral test, we can conclude that our series is convergent. So again, let's ask the question, comparison test applicable ba? Let's try, no? Kasi it might be better to actually use comparison test since bounded is sine 1 over n as we have argued before. So, parang comparable siya sa n squared. Let's try that. So, again, we use the p series, sum from 1 to infinity ng 1 over n squared, which is convergent. So from our previous solution, alam natin na bounded si sine 1 over n by 0 and 1. And we will be using the right-hand side. This right-hand side kasi we want our original an to be less than a convergent series para makonclude natin convergent siya. So dividing both sides by n squared, we will arrive at the following inequality, which gives us a series na mas malaki kaysa dun sa original series natin, and that is the case 1 ng comparison test. So, we can conclude that by comparison test, yung series natin converges indeed. So, again, we have proven using integral test and comparison test kung ano ang convergence or divergence ng series na to. So, we now move on to exercise 3. This time, we are given the sum from 1 to infinity ni e minus square root ni n. So, parang mahirap tong i-integrate. So, let's use comparison test instead. So, maghanap tayo ng series to compare this with. Paano natin gagawin yon? Well, una, i-feel muna natin kung convergent ba siya or divergent. So, kung wari, feeling natin divergent siya. Then, we look for a divergent series to compare this with. So, alam natin na si e raised to square root of n ay greater than n. So, kapag kinuha mo yung reciprocal, pwede mo silang i-compare. So, let's try 1 over n, the harmonic series, which is divergent. So, for n greater than or equal to 1, alam natin na nangyayari to. Since mas mabilis lumaki si e raised to square root of n. So kapag kinuha natin yung reciprocal, we'll arrive at this inequality. Pero meron tayong divergent series na greater than our original series. Pero wala yun sa any of the cases ng comparison test. So comparison test here is inconclusive. Wala kang pwedeng makonclude using this series. So ano na ang gagawin natin? So you either choose a different test or choose a different series. Since ayaw nating mag-integral test, let's try first to think of a series, no? Pero if you think about it, if papalitan ko to ng n squared, mangyayari pa rin to. Pero perhaps mag-iiba na yung restrictions natin for the interval. So let's try that. Let's use 1 over n squared to compare it with. In fact, mafe-feel mong magwo-work to kasi previously we arrived at an inequality which gives us a series na mas malaki, no? So kung convergent yung series na yon, magko-converge din siya. Same thing applies, no? Pero this time, si n is greater than or equal to 3. Mangyayari to at mangyayari na si e square root of n is greater than or equal to n squared kasi mas mabilis lumaki to. And this time, at n greater than or equal to 3, mas malaki na siya comparative kay n squared. So, we have the following inequality after taking the reciprocal. So, we have 1 over n squared greater than or equal to 1 over e squared of n. And since this series, the bigger series, is convergent, it gives us the case 1 of comparison test. So, we can conclude na yung series from 3 to infinity and therefore yung series from 1 to infinity would converge. If you want to try applying integral test here, it might have very tedious calculations kasi mag-apply ka ata ng IBP. Pero you can try it. So let's move on to our exercise 4. This time we are given the sum from 2 to infinity ng 1 over n square root ng ln n. Tapos, mukha siyang easily integrable if you let u to be ln n, no? Ito na kasi yung derivative niya. So, let's try applying integral test. Kasi sa integral test, again, is useful for easily integrable series. So, let's do that. We let f to be 1 over x square root of ln x para si f of n equals sa an on our interval 2 to positive infinity. And clearly, si f ay continuous at positive value dun sa interval natin. And moreover, si f ay decreasing kasi kapag kinuha mo yung derivative niya, we will have this equation. So, after factoring out negative, ang matitira na lang natin sa loob ay puro positive functions, positive valued functions. Hence, we know that this is less than or equal to 0 on our interval. So, we can apply integral test. Moving on sa pag-compute ng proper integral natin, this is just equal to the limit as t approaches infinity ng integral na to. But again, this is easily integrable when you let u to be ln x. And it will give you the following antiderivative, 2 square root of ln x. If we evaluate that from 2 to t, we will get 2 square root of ln t minus 2 square root ni ln 2. So if we approach t towards infinity, si ln t pupunta din ng infinity. So our entire first term pupunta sa infinity. And this is just a constant. So finally, yung proper integral natin would just be infinity. Since ang ating improper integral ay equal sa positive infinity, that is the case 2 ng integral test, we can conclude that our original series is also divergent. Okay? Kaya bang applyan ng comparison test? Buka, pero you can try. You can try doing it. So, yung goal mo this time would be to compare it with a divergent series. But for now, let's move on to our next exercise. This time, we are given the sum 2 to infinity of ln n over n cubed. Parang hindi siya kaagad na i-integrate. So, try muna natin yung comparison test. Hahanap tayo ng series to compare in here. So, hanap lang ako within that, no? Nakakakita tayo ng 1 over n cubed, which is a p series. So, that's a good choice, 1 over n cubed. You can try that. Pero, if you remember na meron tayong bound sa ln n, then you might want to change that into 1 over n squared. Okay. Sa comparison test, if you don't have an idea what series to use for comparison, you may want to start with bounding your functions, especially if you have bounds for your functions involved in an, then you might want to start with those bounds tapos palabasin nyo yung an. So, for example, alam natin na for n greater than or equal to 2, si ln n is less than n minus 1, which is less than n. So, pag dinivide natin by n cube, makukuha na natin si an. And n over n cube is just 1 over n squared. So we have a convergent series which is greater than our original series, that is case 1 of comparison test. So we can conclude that the series converges. So we can now move on sa exercise 6. So we are given the sum from 1 to infinity ni tangent inverse n over 1 plus n squared, which is easily integrable. So let's apply integral test. Bakit siya easily integrable? Kasi si tangent inverse ni n, yung derivative niya ay lumilitaw dito sa an, which is 1 over n squared, no? Ay, sorry, which is 1 over 1 plus n squared. So, but let's let f to be tangent inverse of x over 1 plus x squared. So, yung f of n natin is equal to an on our interval 1 to infinity. Clearly, this is continuous on our interval. As for positive valuedness, pwede rin tong 1 for as long as x is greater than 0, strictly, si arctan ni x would be between 0 to pi over 2. Pero kaya nire-restrict natin siya sa 2 kasi kapag kinuha natin si f prime, mangyayari to, itong 2x tangent inverse of x would be greater than 1 at some point, and that point is 2. So this is less than or equal to 0. So fr is decreasing. So, ang conclusion natin, since na-satisfy yung lahat ng conditions, is that our integral test is applicable. So, let's apply it. So, evaluating this improper integral, we just take the limit as t approaches infinity ng integral na to, which again is easily integrable since if we let u to be tangent inverse ni x, nandito na kaagad yung kanyang derivative. So, ang antiderivative nito, if you wanna try, would become tangent inverse x squared over 2. Now, evaluating that from 1 to infinity, we get tangent inverse of t squared over 2 minus tangent inverse of 1 squared over 2. If we approach t towards infinity, tangent inverse ni t would become pi over 2. Squaring that, you get pi over 4 divided by 2 is pi over 8. Ito yon. Tapos, tangent inverse of 1 ay pi over 4. Squaring that will give you pi over 16 divided by 2 is pi squared over 32. So finally, our improper integral would just be equal to 3 pi squared over 32. So yung improper integral natin nagko-converge, which is case 1 ng integral test, and so we can conclude na ito ay convergent, itong series na to. Pero ang given series natin, original, ay from 1 to infinity, but it also converges. Okay? So we can move on now to exercise 7. So we are given the sum from 1 to infinity ni 2 plus negative 1 raised to n over square root ni n. So we might not want to use integral test on this one. Let's use comparison test kasi pangit siyang i-integrate. Okay? So maghanap tayo ng series to compare this with. And for that, let's look at the bounds ng mga functions involved. Yung taas, nagigilang siyang 1 or 3 depending sa parity ni n. That is, kapag even siya, nagigitong 3. Pag odd siya, nagigi siyang 1. So, parang mako-compare mo itong series natin na to 1 over square root of n. So, let's do that. We will compare this series to the divergent P series, 1 over square root of n, and from 1 to infinity. So, first, again, alam nating bounded yung taas by 1 or 3. Strictly speaking, equality sila depending on the value of n, pero it's not wrong to say that this 2 plus negative 1 raised to n is between 1 and 3. Pero we're just gonna use this left-hand side. Why? Kasi we want our original series to be greater than 1 over square root of n para meron tayong conclusion based on comparison test. So let's use that to arrive at this inequality after nating i-divide both sides by square root of n. So again, meron tayong series na mas maliit kaysa sa original series natin, and yung mas maliit na series ay divergent, which is case 2 ng comparison test. So we may conclude that our series diverges as well. Okay? So for exercise 8, we have a similar series. Just this time, yung denominator niya ay n square root ni n or n raised to 3 halves, no? So, we can actually apply the same logic from previous solution. This is still bounded, so we might want to compare it with the convergent p-series 1 over n raised to 3 halves. Ano yung magbabago from our inequalities from the previous solution? Ang magbabago lang is that si square root of n magiging ng n raised to 3 halves. So, eto pa rin siya. We have the same inequality for 2 plus negative 1 raised to n. Pero this time, since convergent yung kino-compare nating series with our original series, we will use the right-hand side. That way, mag-arrive tayo at this inequality, giving us a bigger series na convergent. Kasi you can factor out 3, so convergent pa rin siya. Therefore, since case 1 yun ng comparison test, we can conclude that our series is also convergent. So let's move on to exercise 9. This time, meron tayong sum from 1 to infinity ni 2 raised to 1 over n squared. And this is easily integrable, no? Kasi you can let u to be 1 over n. Tapos yung derivative niya is negative 1 over n squared. Nandito na siya. So, let's let f to be 2 raised to 1 over x squared since gusto nating i-apply si integral test. That way, si f of n ay equal sa an on our interval 1 to infinity. So, it's clear naman na positive valued siya and continuous on 1 to infinity. So, we can now proceed with taking the derivative, which is just this equation. Pero palitan nyo si n ng x, okay? So, pwede naman nating i-factor out yung negative and still, no, x dapat yung mga to since we are taking the derivative of f. So, this is, so lahat ng terms on our derivative are positive naman. So, if we multiply it by a negative, we will have something less than or equal to 0 on our interval. So, decreasing siya. Hence, yung integral test natin is applicable. We now proceed with evaluating this improper integral, which is equal to the limit as t approaches infinity ng integral na to. But again, this is easy to integrate kasi if you let u to be 1 over x, you will just arrive with this antiderivative, which is 2 raised to 1 over x over ln 2, negative nun. Tapos i-evaluate natin from 1 to t, giving us negative 2 raised to 1 over t over ln 2 plus 2 over ln 2. Now, if we want to now if we approach t towards infinity, si 1 over t magiging 0. So, si 2 raised to 0 ay magiging 1. So, we have negative 1 over ln 2 plus 2 over ln 2 giving us 1 over ln 2. So, yung improper integral natin converges. So, by the integral test, case 1, yung series natin is convergent as well. Okay? On to our last exercise for this discussion. We have the series n plus 3 raised to n over n plus 2 raised to n, where n runs from 1 to infinity. So, parang pangit siyang i-integrate, no? Gawin na lang natin yung comparison test. Maghanap tayo ng series to compare this with. Pero parang mahirap mag-isip readily, no? We have choices. Meron kang nakikitang 1 over n dyan. Meron kang nakikitang 1 over 2 raised to n, 3 raised to n, which are geometric series. Pero let's try 3 raised to n over 2 raised to n, no? So, let's use this geometric series. Bakit yan magwo-work? Pwedeng hindi mo muna ito ilagay. Pwedeng mag-proceed ka muna with the inequalities. So, it's good to note that 2 raised to n, lagi siyang mas malaki sa n for n greater than or equal to 1. Kasi exponential to, no? So, mag-i-increase siya rapidly. Tapos, meron tayong ganitong relationships. Paano yan nakuha? Okay? So, mag-start muna tayo sa an. So, kapag tinanggal ko yung n sa numerator, liliit yung numerator ko, so liliit yung buong quantity. So, meron tayong ganitong relationship. Yung an natin greater than or equal to 3n over n plus 2 raised to n kasi tinanggal natin yung n sa taas. So, this time, no, kung si n sa baba naman, papalitan natin ng 2 raised to n, and alam natin na si 2 raised to n mas malaki kaysa kay n, so lumaki yung denominator natin, meaning liliit yung quantity natin. So, ito should be greater than or equal to 3 raised to n over 2 raised to n plus 2 raised to n. But what is that? That is just 3 raised to n over 2 raised to n plus 1, which is just 1/2 times 3/2 raised to n. And alam natin na ito ay nagda-diverge kasi geometric series siya na ang ratio natin ay greater than 1. So, meron kang mas maliit na divergent series from our an, no? So, by the comparison test, case 2, magda-diverge din yung original series natin. Okay? So, that serves as the end of our discussion. Thank you for watching, and I hope you learned something from this.